So far we've been talking about the operation of this stretch reflex under pretty much one set of circumstances, but there may be a variety of circumstances that would demand a change in the sensitivity of these receptors. So it makes sense that there ought to be some way to change the sensitivity of these receptors even during an active movement. And this is where the input from the gamma motor neuron to the contractile elements of the intrafusal muscle fibers comes in. So let's consider how this works. First of all, what do I mean by gain? Well, what do I mean by gain is simply this. Gain is the amount of extrafusal muscle contraction that can be elicited by a given stretch or a given load that's applied to that muscle. So it's basically an assessment of the output of the motor unit relative to the input in the form of a sensory signal that is monitoring the length of the muscle. So if gain is low, then one can imagine that a moderate stretch will induce only a rather modest output from the central nervous system, leading to only a small increase in resistance given a particular load that's just been applied. If gain is high, then you can imagine that the very same sensory stimulus will now elicit a much greater number of action potentials in the motor output to the muscle that was stretched, and a much larger increase in resistance given the very same sensory stimulus. So gain is a way of either dialing up or dialing down the volume, if you will, of this stretch reflex circuitry. So how is gain adjusted? Gain is adjusted by the output of our gamma motor neurons to the contractile elements of our intrafusal muscle fibers. So one way that we can think of how this works is that activating our gamma motor neurons resets the sensitivity of the muscle spindle. And this would be especially important if the muscle is actively contracting, meaning that the muscle spindle is getting shorter. Well, if it gets shorter, then it loses its sensitivity to monitor the change in muscle length. So let's look at this figure and see how this might actually work. Now, for the purposes of this schematic, we're taking the intrafusal muscle fibers out of the muscle. Of course, they're actually embedded within the muscle, but for this demonstration, let's just simplify by removing these intrafusal muscle fibers. And what we can see now is that if we have a microelectrode that can stimulate the extrafusal muscle fibers, then this muscle can contract against some load. And if we do nothing to the muscle spindle, what we would see is that during the active contraction, the muscle spindle would grow silent. And that's because there is shortening of the muscle. And as the muscle shortens, then this intrafusal muscle fiber becomes somewhat lax. And that reduces the stretch that would be applied and reduces the sensory outflow from that group 1A or group 2 afferent that happens to be supplying that muscle spindle. Now let's imagine that we repeat this experiment, only now, while we stimulate the alpha motor neuron, we also stimulate the gamma motor neuron. So here's the stimulation of the alpha motor neuron and concurrent stimulation of the gamma. So notice what's happening here. As this muscle is contracting and getting shorter, the activity recorded from this spindle afferent is filled in. And so this muscle spindle can remain sensitive to the dynamic aspects of length change, even while that overall muscle length is getting shorter. Now, these adjustments of gain, they can happen in lots of different contexts. In fact, they are probably happening all the time, and this can be highly adaptive because we move in a variety of situations with a variety of goals in mind. So the adjustments of gain are very much context dependent. So the gamma motor neuron activity can be adjusted relatively independently from the excitability of the alpha motor neurons. And this can largely be accomplished by descending inputs that are coming down mainly from the brainstem. We'll talk more about that in a subsequent tutorial. But note that the gamma motor neurons are key to adjusting the sensitivity of the muscle spindle. And that adjustment of sensitivity is itself something that can be governed from above. And you might imagine that this could be very important as we engage, for example, in sport, or perhaps as we're engaged in circumstances that require some sense of fight or flight. We can imagine that an increase in muscle spindle sensitivity is very good for generating explosive kinds of motor activities. So, for example, imagine being a sprinter on the blocks, ready to go when the starter pistol ignites. So we are ready, we're set. Well, we imagine that the gain of our muscle spindle system is probably increased during those moments of getting ready and set, because what we want to be able to do is to monitor a change in muscle length that might happen during this explosive outburst of motor activity that a sprinter would engage in as they exit the block at the sound of the starter's pistol. Well, that's just one example of how descending inputs can modulate the gain of gamma motor neurons. These adjustments very well may rely on descending inputs from the brainstem from parts of what we call the reticular formation of the brainstem that generate and then release in the spinal cord biogenic amine neurotransmitters. So these are transmitters that we consider to be neuromodulators because they have the effect of either increasing or decreasing the excitability of their postsynaptic targets. This is exactly what we might need if we're going to adjust the excitability of our gamma motor neurons, depending upon context. There's even evidence to suggest that the presynaptic terminals of our group 1A afferents themselves are subject to synaptic inhibition, and this would be a means of cutting off the incoming sensory signal independently of whatever adjustment of gain we might employ at the level of the gamma motor neuron. So either by adjusting the sensitivity of the spindle or perhaps interrupting the incoming sensory signals derived from that spindle, we can make the overall sensitivity of this muscle spindle system and its impact on the extrafusal muscle fiber something that can be exquisitely controlled. I think the power of gain control can be easily demonstrated. If any of you are athletes or you participate in stretching activities either before or after some sport or some kind of activity involving exercise, you may be wondering, well, how is it that we can voluntarily stretch? I mean, maybe some of you do yoga or something like that. The fact that you can voluntarily stretch a muscle implies that there must be some kind of way of adjusting the gain of those muscle spindles, because obviously you actually want to lengthen those muscles. You don't want that spindle to contract against your voluntary desire to lengthen that muscle. So that implies that there must be some descending control that will adjust either the gain of the muscle spindle via changing the excitability of the gamma motor neuron and or interrupting the incoming afferent signal that's arriving via that group 1A or group 2 afferent in the spinal cord. All of these considerations that we've been talking about so far pertaining to the muscle spindle are really critical for maintaining muscle tone. So muscle tone is simply the resting level of tension in a skeletal muscle. And this tension depends upon the firing rate of the alpha motor neurons that supply the extrafusal fibers of that muscle. The activity of those alpha motor neurons is what's regulated by the sensory feedback that's coming from the muscle spindle. And as we've already discussed, the gamma motor neuron then will be really critical for adjusting the sensitivity of that muscle spindle and therefore the sensory signal that is then impacting the output of the alpha motor neurons and therefore the tone of the muscle. You can imagine that if there is damage to the alpha motor neuron itself or the axons in the ventral root or the spinal nerve, there should be a catastrophic collapse of muscle tone, because those muscle fibers no longer are receiving their electrical signal from the central nervous system to maintain their resting level of tension. One might also imagine that there would be a catastrophic loss of muscle tone if there should be a disruption of the incoming sensory signals via the dorsal root. And that incoming sensory information is essential for maintaining the output of those alpha motor neurons. So damage either to the ventral horn, the dorsal horn, the ventral root, or the dorsal root, or perhaps the spinal nerve itself, all could produce a catastrophic loss of muscle tone. We call this hypotonia, or sometimes we call the muscle itself flaccid to refer to this catastrophic loss of muscle tone. Now, we'll see in a future tutorial that if there's damage not to this reflex circuitry of the spinal cord, but to the inputs that are arriving from higher levels, such as the brainstem or the motor cortex, one can eventually see exactly the opposite response, an increase in muscle tone. It's as if the gain of these segmental reflexes is turned up by a loss of descending inputs. And this difference between seeing loss of muscle tone or an increase of muscle tone will be absolutely critical for your assessment of the localization of injury based on an examination of skeletal muscle and the status of our segmental stretch reflexes.